In the previous lectures in both neuroscience and programming, we covered just the basics of how to use Python, what were variables, data types, functions, classes, and so on. And on neuroscience side, we covered the main brain areas, how a neuron works, how they communicate with each other, the spikes, synapses, and such. And we covered just the basics of, yeah, all of this. And then last week, last Saturday, we started to combine these two fields of programming and neuroscience. Let me very briefly cover again what we said last week and maybe add a few details here and there. And this time, we will actually get into the right implementation of it. So this time, we'll be writing Python code that will allow us to somehow understand and make sense of our brain's activity. So, in the previous week, like I mentioned, this is the device that we will be using. This is called the Neurosity Crown. It's an EEG, electroencephalogram, which basically means that, so you remember when we were talking about synapses before, every time neurons they build up a certain amount of charge, and then they shoot out this charge with a spike, and that's how they communicate. And this buildup of charge can be detected by these devices. And so what would happen is if I put this on like this, depending on where these electrodes go, like or where on my head, they'll be measuring activity in different areas of my brain. For instance, here we have visual cortex, here we have a motor cortex that controls our hands and even our mouth and every muscle of ours and so on. And so with this kind of device, we can see what kind of activity we have in these areas, and I can use that to figure some things out, like to find out if we are focused, distracted, if we are thinking of moving our right index finger or our left leg, and then map this to whatever we want. Like an easy example, I mean, simple, but not easy to do. Example is maybe even in gaming, like, you know how you had to click the right keys to move forward or back and such? Like instead you could move telepathically, or you could type text telepathically. You could communicate with people telepathically. Like you can imagine for someone who is paralyzed and not able to use their hands, this can be very useful, especially for someone who can't even speak, like severely paralyzed people who, yeah, are having serious problems with communication, like Stephen Hawking kind of cases. Such people would benefit a lot from having these kinds of devices, but only if they have high accuracy. So, yeah, we'll just see how we can use this one from Python. There are other devices as well, like a ton of them out there. Some are EEGs like this one, some use magnetic fields, some use muscle activity instead of your brain activity. Like there are many different ways, but we'll just focus on one example for now because this just happens to be what I have on hand. And yeah, basically that's it. If you have any questions about previous weeks or anything or something about this lecture, feel free to interrupt me either verbally or by writing in the chat, whichever way you prefer. And yeah, I'll try to answer it as much as possible. Okay, let me share the screen. So, just a brief overview of our last lecture stuff, just in case someone wants a refresher. So we were talking about how we might look inside the brain. So we said that there's a couple of ways, depending on how expensive we can make the equipment, depending on how invasive we allow it to be. Invasive basically means how much you drill down your skull. So, for instance, this is non-invasive because I can just put it on and put it off just like that, no issues. But a lot of the brain chips that exist, you literally have to drill your skull and then take off some of your skin, take off some of your fat and whatever, and go all the way inside your brain and then either put it on the surface of your brain or even cut out some of the brain to put it deep inside the brain. So that would be very invasive. So there's different levels of invasiveness, and obviously less invasive is more comfortable and easier to also get legally approved and so on, and safer too. But more invasive has better resolution, more level of detail. Because I mean, fundamentally, if you think about it, Any signal that this thing picks up on has to go from my brain through my skull, then through my skin, then through my hair, and then arrives at this device. Like hopefully not too much through hair if I put it on properly, but still, like there's a lot of layers it has to go past. And because of that, the signal that this one picks up might not be very accurate. Like I might not be able to tell, was I thinking of moving this finger or this finger? But it is good enough that I will be able to tell if I was thinking of moving this hand or this hand. So it depends on what kind of resolution we need. So different kinds of methods exist. There's magnetic encephalography, there's EEG, which is this. There's near infrared spectrography, there's this, there's that, and we will cover a few of this, but yeah, our actual use will be just with the EEG because it's one of the cheapest options and also just easier to use pretty much. So levels of invasiveness. So as you can see, EEG is not invasive at all, it's on the outside. Then there is ECOG. ECOG is when you take off your skull, but then you put your electrodes or the measurement devices on the surface of your brain without actually cutting through the brain. Then there's multi-electrode arrays, which go directly inside your brain, in which case you have to cut through some of your brain tissue and you do some permanent damage, and that's bad, but some treatments require this. Like the Neuralink's brain chip uses this kind of thing. So basically they destroy some of your brain, but in exchange they can read things in more detail. You can similarly do single cell recordings, like put a very small electron in your brain that will record the activity of just one neuron. That won't be very useful generally, but it could. There is also fMRI, which is the MRI machine is a giant magnet, basically. You put your head in it, and it will detect the blood flow of your brain, which carries a magnetic field to it because blood has iron. And yeah, basically based on that, it can image your brain and understand in 3D exactly what's happening in your brain. But the downside is that it's a bit slow because blood needs time before it gets to any part of the brain that you're activating. So you won't be able to use it to play a game or control a robot arm because it will be like a few seconds delay from when you thought about something and when it actually understands it. So I'm just rushing through this because I'm doing a reminder from previous week, but if you have any questions, feel free to interrupt me. Okay. So Neuralink is one of the most famous, or maybe the most famous brain-computer interface companies right now. It's Elon Musk's company, and they do brain chips which they put in the motor cortex of a paralyzed person, which allows them to see, oh, this person was thinking about moving his hand or thinking about moving his finger like this. And based on those signals that they pick up, they have this person, people then use a computer, use a keyboard, use a mouse, that kind of thing. So instead of typing on the keyboard or moving the mouse, they think about doing that. And pretty much by that, they are able to. All right, let me just very briefly cover this again. So Neuralink chips are put in the motor cortex of a paralyzed person. It allows us to understand what kind of movement signals this person was sending. And based on that, we can help them to use a keyboard, use a mouse, communicate to a computer. There are also some companies that pretty much using the similar method allow people to control robot arms. We'll see that in a second. In fact, let's see that right now. Just very briefly. So this woman.
So this is the most complex robotic arm in existence today. You can control that using thought in the brain.
I won't go into too much detail of this, but
already raising serious social and ethical questions.
There's a lot of interest in how this is affecting the way we evolve.
The fence, hospital, and worse, breaking days.
so for someone who
Go about my-
might lose an arm, they can then basically telepathically
That would
control
have
it.
to do with your hand.
The modular prosthetic limb, or MPL,
So essentially, the idea is just as you would send these commands to your fingers, you now instead send these commands to a robot arm. And you can then either attach this robot arm to yourself or even remotely control a robot arm that is in another room or maybe even in another city. For instance, this can allow some doctors to do surgery without even being in the same city. And yeah, all kinds of interesting applications like that. So this is both to help someone who lost an arm or is paralyzed, but also even if you're not, it can allow you to remotely control arm in a place where you're not physically present. So there's a lot of interesting use for this kind of technologies, basically both for recovery and augmentation of some kind. This was the main idea I wanted to show. But interestingly enough, with brain-computer interfaces, it's also possible to give you a sense of touch for this arm. So typically, obviously, if someone touches this arm, I won't feel it even if I'm remotely controlling it. But that's because in our brain we have motor cortex here, and right behind that we have a sensory cortex. And think somatosensory cortex. And somatosensory cortex is where we have a feeling of touch. And generally, like when I touch with my finger on something, like say on a screen or wherever, I will feel this touch because the signal will flow from my finger all the way through my hand, then through my spinal cord, and it will go all the way up into my somatosensory cortex. And I actually feel touch here, not literally here, which is why anesthesia works, for instance, because it cuts off this signal. So similarly, what some people do is they have a robot arm, maybe even in another room, and this robot arm, when touched, sends a signal, like through the internet or Bluetooth or something like that. And then this person might have a chip installed on their somatosensory cortex. And this chip will stimulate the somatosensory cortex so that this person will feel as if he was touching something himself. And with that, some paralyzed people actually have robot arms on which they actually feel touch. And so they use it like a normal arm. It's less accurate than a normal arm, but it's better than nothing. And it can always improve, potentially even beyond the normal capabilities. So this is just one possible example. And other examples include, this is just a Neuralink chip structure. And just other examples also include vision help. So basically, Neuralink, this same company, also has this project Blind Sight, which is not ready yet, but they think they'll have a first patient in a few months, where basically they want to cure blindness. So, as you remember from previous lectures, the way vision works is that light hits our retina on our eye. It gets focused into the photoreceptors that we have inside our eyes. These photoreceptors are a type of neurons, which will then spike based on this light. And then this information is carried through the optic nerve, goes to the thalamus, and then into our visual cortex. And then in the visual cortex, we make sense of what we saw. So if you are blind, it's either because you have damage on the eye or in the optic nerve somewhere. So Neuralink people thought, well, what if instead we send artificial signals to the visual cortex based on some of what readings a camera had? So they are working on this device that will see things like a camera and then will send the correct kind of signals to your visual cortex to allow you to see. They say that at first it will be like black and white and very lame version of vision, so to speak, like very low resolution and not that good. But over time it will be improved. It eventually will have color vision. And then once it gets good enough, it could even do infrared vision or ultraviolet vision. So basically kinds of visions that regularly the eye does not have. So again, basically all of these technologies start as recovery to help people who have some kind of illness to basically go back as close as possible to baseline level. But then these same technologies will very quickly move us into augmentation territory. So augmentation can be cure pains, cure some kind of mental illnesses, slow down or cure maybe even like Alzheimer or schizophrenia or epilepsy, and then augment our mind in some strange ways, like maybe enable us to see more color spectrums, enable us to hear more, enable us to maybe even feel touch in higher resolution or something like that, enable us to control robot limbs, enable us to learn faster, control our emotions, control our cravings, like all kinds of strange applications. Basically, every cognitive thing that we humans can do, like thinking, feeling, learning, moving, everything, can be augmented in some strange way. And maybe we can even unlock new senses or new things. Like, for example, about new senses, basically, anything that can be measured could, in principle, become a sense. So, for example, light is being measured by our eyes and translated into brain activity. So then we see. Similarly, vibrations in the air are translated by our ear into sound. And that's how we hear music or make sense of what words someone told us. Also, similarly, we have touch, smell, hearing, touch, smell, taste, sense of balance, sense of temperature, so on. It is believed that, not believed, but like demonstrated already, that we can also add new senses if we want to. For instance, what some people do, I'm not endorsing this, but what some people do is they put a magnet in their finger, a small magnet, and because it touches on the nerve, every time they go near a magnetic field, like just electricity in your house, power lines, metals, or something like that, this magnet vibrates a little, and at first it feels like just random sense of touch, doesn't mean anything. But after a couple days, your brain adapts to it because of neuroplasticity. And then you start to make sense of this new magnetic sense. And so after that, whenever you walk into a new building, you know, oh, electricity goes here. Oh, phone is charging. Oh, microwave is turned on at this power level. Oh, power lines here must be like this. Oh, there's titanium in this room. Oh, there's iron in this room. So basically allows us to have a new kind of sense. And it's not sense of touch or seeing or sight or hearing or anything. It's a new kind of sense. And so similarly, many strange kinds of augmentations could exist in the future as well. And also strange new capabilities like this Neuralink wants, for instance, to do ability to directly send knowledge between brains. So for example, right now, if I know some programming and if I want to teach you programming, I have to somehow figure out how to translate this knowledge in my head into words and then explain it to you in words. But in theory, it should be possible to just take the knowledge directly that I have in my brain, which is not quite words, and send this knowledge itself to your brain. So Neuralink thinks that eventually they'll be able to do it. On a very small level, it has been demonstrated in mice that very simple kinds of knowledge you could directly send from one brain to another. It's a work in progress, but in theory, yeah, that could allow us to basically know anything where someone is willing to share instantly. So maybe a 100-page book you could learn instantly and so on. But to come back to reality, currently most of the use of brain-computer interfaces is to help with illnesses, help with pains of different kinds, help maybe a little bit with memory loss, and to help with controlling prosthetics. Could be for paralyzed people or could be for just even healthy individuals who just want to have robot limbs controlling or something like that. All right, am I going too fast or am I clear?
No, you're clear.
Okay. All right. So briefly, there's different levels of invasiveness. Non-invasive is, for example, our EEG. ECOG, which goes on the surface of your brain, is less invasive. And anything that goes inside your brain is more invasive. That's the idea. So this is ECOG when you go on the surface of your brain and you map out M is for motor cortex, S is for sensory cortex. So basically here we give orders to move our body, here we feel touch and so on. So like depending on what you want your implant to do, you would put it in the right place. Also, if you want to go inside the brain, you have to consider what you have to go through. So at first we have our scalp, which is basically the skin on top of our head. Under that we have a skull, which is the bone that protects our brain. Under the skull, between the skull and the brain is three tissues which are together called meninges. So there is dura mater, arachnoid matter, and pia mater, and it's called subarachnoid space. And basically, these are like sponges to make sure that anytime a little click happens on my skull, I don't instantly get brain damage from it. So the reason why this doesn't give me brain damage is because these ones basically cushion it so that brain doesn't receive as much shock, because brain is very delicate and yeah, we want to avoid damaging it as much as possible. Like over time, boxers still get brain damage sometimes, but as long as you don't box, you should be generally fine because these sponges will protect you. So when they want to do invasive brain implants, they have to cut through all of this and get to the brain. So ECOG, for instance, cuts right around here down to arachnoid, but not all the way there. But Neuralink kind of implants have to cut through everything and go to inside of the brain. I mean, this one doesn't cut at all, so it's fine. There's also Synchron, a brain company that brings inside your signals through the jugular vein, so that they don't have to penetrate your skull, but basically does the same job. I will send the link to this in the description. It doesn't matter too much right now. You can also see details of it in our proper discussion of this from our last lecture. Let's move on from now. fMRI is just magnetic fields to see how your blood flows through your brain. There is also a new application of ultrasound, which is basically sound at high frequency, which allows you to also scan your brain and even stimulate your brain, so do different operations on your brain. This is one company that uses ultrasound and they want to cure basically all mental illness, or at least starting with curing chronic illnesses like chronic pains and anxiety and depression and PTSD, they say. They say the product will be ready in like 5 years and will look like headphones and will cost like $1,000. Let's see. And yeah, most importantly, EEG, our today's discussion. So briefly, how it works. When neurons talk to each other, they spike, which means that they build up voltage and then they shoot it out. This buildup can be detected when enough neurons side by side do it at the same time. And this EEG has different regions. Like depending on where each of these electrodes go, they have a different name. For instance, right here we can see the center line ones have this subword Z. The right ones are even numbers, left ones are odd numbers. Closer it is to the center, the small number it is. And also, so the forward ones are frontal lobe measures. So we have F. So this place is FZ. This would be F2. This would be F3 kind of thing. So to the back, then we have C for central, T is for temporal lobe right here, P for parietal, and to the back we have O for occipital. So for instance, for this, these two are for the occipital lobe, these ones are for parietal lobe, these ones are frontal. And so depending on where they are, where they go on my head, they do different jobs. Some measure my visual cortex activity, some measure my motor cortex, and so on. But for measuring things like focus, in theory, any of them could work because focus looks similar throughout the brain. So this is the Neurosity Crown. It can measure your focus level, your calmness level, just raw brainwave activity, or what kind of movement commands you give out. Mostly we deal with brainwaves. So brainwave, what it means basically. Every neuron in our brain fires, let's say, maybe 5 times per second, 1 time per second, maybe less often than that, maybe more often than that, but like at some set speed. Typically, in our working life, our neurons fire at somewhere from 12 to 30 hertz. So hertz means times per second. So if a neuron fires 10 times per second, that's 10 hertz, and so on. So typical is beta waves, which is from 12 to 30 hertz when we are thinking, speaking, and so on. If we're a little bit distracted or relaxed, it's alpha waves from 8 to 12 hertz. In sleep, we have theta waves from 4 to 8 hertz. And in coma or deep sleep, we have delta waves from 0.5 to 4 hertz. And if we're very strongly focused, like playing chess or something like that, then we have gamma waves, which is from 30 to 100 hertz. And basic idea is if you want to know how focused someone is, you can just see how much beta and gamma waves they have versus how much alpha and theta waves they have. And you can basically just divide the amount of these waves on the amount of these waves on your brain to get focus level, roughly. So this is the idea, theta to beta ratio. So basically, if you have not many theta waves and many beta waves, that means you are very focused. But if you have more theta waves, that means you're less focused. And you can then use this to gamify how to learn focusing by using neurofeedback. So the idea with neurofeedback is this is a strange phenomenon where if you see a visual representation of some phenomenon in your brain, like suppose of your focus level, then you intuitively figure out how to control it. So for example, if on the screen I show you a ball that grows larger when you remain focused, but then if you get distracted, it shrinks, you intuitively figure out how to make this ball larger or smaller. And what that means is that you're learning how to control your focus level. This also applies to controlling your feeling of pain and a few of the other things. So this is called neurofeedback, this strange phenomenon. We'll mention it a bit more, but yeah, that's the main idea. And yeah, there also exists a brain stimulation method called transcranial direct current stimulation. Basically, electric shock on your brain at the right places. Some American military organizations are experimenting with this to see if they can teach their military people faster. So, for example, they were experimenting with the idea of what if we scan the brain of an experienced pilot and then a beginner pilot who's learning right now. What if we stimulate the brain of a beginner pilot in the same places with same kind of activities? Maybe that could help the pilot to learn faster. And some studies showed that with the right kinds of stimulations, they could speed up learning. They can't make it quite instant, but they could speed it up a couple percentages. So this is still a work in progress. We don't know how far this can be pushed. We don't know if it is or it isn't possible to just maybe in a few seconds transfer years of knowledge or a 100-page book or something like that. Might be possible, but we don't know yet. All right, this is a brief overview of what exists. I mean, a little bit more than this exists, but this is a very brief overview. We dived into a little bit more detail in the previous lecture. But now, for this lecture, I want us to focus on exactly how to connect to this device from our code and what we can do with it. Okay. So, in fact, let's start by going to console neurosity.co, which is a website where I can see the activity of this device. And just briefly go in. So right now it's disabled, so nothing's going on. But I can still see, like here you can see, these are the channels on this device. So they are named based on where each of these electrodes go. For instance, when I put this on, some of them are on my frontal lobe and so on. So for instance, this PO3 and PO4 are these two, because they are at the border between parietal lobe, which is here, and occipital lobe, which is here. So they are right here. So I have PO3 and PO4 on names. And so when I put this on, I will be able to see what each one of these places picks up as the signal. So let me just turn on this device, and we'll start to see. This device connects with Bluetooth to a phone, and then from the phone we can connect it to the internet. I'll show you how it's done in the phone in a second. First, let's see where we can activate it. So the way we do it is, in fact, let me show you how we do it. I'll now share my screen from my phone to show this. But first, before that, I just want to briefly show what this place looks like. So here, if we start it, I mean, okay, right now we don't have any signal because we're not connected, but you can see the names here of each of the areas of this thing, like each one of these. We can see them right here. So we will see the activity of each spot displayed here. Then we will be able to do some things with it. We will be able to take some measurements of how calm I am and so on. Here it will show us how well I'm putting this on. And then we would also be able to train it to recognize what it looks like when I'm moving my left hand or something like that. They also have an emulator, which means that even if you don't have the physical device, you can still test your code by simulating this device. Yeah, some data and stuff. Okay, most importantly, these are the parameters of my device. The name, the channels. Channels are called basically locations where we are measuring. And yeah, some details. And then through the code, right here, we will see how we can connect to it. So first, even without connecting to the device itself, I can connect to my account. By the way, what's going on in this code right here? So I am importing some libraries that we will need for this. So first of all, there is Neurosity library. And from there, I only need Neurosity SDK. SDK, by the way, stands for Software Development Kit. So just something that helps us with coding. And Neurosity SDK is a piece of Python code that will allow us to connect to this device and make sense of it and make use of it. So we need to give it the device ID and just my account's email and password. So I have them written in this .env file right here. They look like this. So Neurosity email equals Neurosity password equals Neurosity device ID equals. And so what I do is I just say, I want to connect to Neurosity SDK. Device ID is give me the environment variable with this name. And I want to log in with the email under this name and password, whatever I have under this name. And then just give me your status. And so for instance, if I run this code, this is what it says. This must have been the last time it was connected. Yeah, because it says Q students, because I was in Kutaisi at the time when I connected it last time. But basically, this says just last time when I connected, what my battery was, when it happened, what Wi-Fi I was connected to, and so on. Yeah, there's also a lot of actual things that we can measure with this. All right, our meeting will end in a moment and we will rejoin, and then I will show how we connect to this device from the phone. But first, briefly, the things that we'll cover is how to take just raw brainwave reading, how to check the level of focus or calmness that we may have, and how to check if I am about to move my left hand with it, my right hand, and so on. We'll discuss how each of those work in a moment. Yeah, this is the main idea I wanted to show. And if you have any questions, feel free to ask at any moment. And yeah, we'll get right to it after the meeting ends. The screen on my phone. Now I will show you what I meant.
Recording it.
I'm just briefly signing in here. And now here, you can see that I already see my crown, as I'm connected to it. And now I can connect it to Wi-Fi as well. Okay, I'll see if there might be a problem. Anyway, so now that we are connected to the Wi-Fi, we should be able to see the activity of Crown from both our website and even in code. So again, this is the device, the channel names, the device ID, and so on. And we just connected it to Crown. And also we see here that it's on 23% charge right now. It is enough charge to last us this time, but yeah, in total the Crown lasts for about maybe 2 hours of activity or 3 hours, and then it needs to be charged. So in that sense, it's still work in progress, but it's enough for prototyping. And by the way, this app is designed to help you with focus and meditation. That's why they have these buttons here. Basically, you put on the Crown, it tells you how well you are focusing. Maybe it even turns on the music depending on your level of focus, changes the music a bit. That's called neuroadaptive music. And yeah, basically it tries to help you remain in high level of focus and also helps you meditate better. That's the idea with this app. But also some programmers use it for gaming and such. All right, now that we connected the crown to the internet, we can go back to our machine. Now that we connected it, when we come here to the Neurosity website, we can see that it's green. And we can see that it's on 20%. Let me just plug it in right now, in fact. There, I just plugged it in my Type-C charger. It'll charge, it's fine. It's online, it's on my home Wi-Fi. And because it's online, we can also start to see activity from it. Right now, it'll be random noise. Oh, it's charging. Let me just unplug it. So right now, the activity of each channel won't really mean much. It's going to be mostly random noise at first until I put it on properly. But you can see, like, we see what each channel, meaning each location, picks up. First, it's not that good. It needs a second to calibrate properly. Also, apparently my home's Wi-Fi might be blocking a lot of the signal. We'll see that in a moment. I'll just change internet in that case. But basically, here, for instance, once I put this on, this can tell us how well each of the signals are being picked up. And based on that, I can just keep adjusting it on my head until signals are good enough. Okay, it's reasonably fine now. We can stop this. Now, if we look at our brainwaves, it should look a little bit more meaningful. This is noise when I move my head and such. Well, basically needs a little bit of calibration to set it up properly. And there you can see each place measures its own unique neural activity. And based on that, we can start to make sense of it. Okay, now enough looking at it here. Let's actually look at our code, what we can see in our code. So we can just log in to our device and see the status. Here it will tell us that we are on Mauritius Wi-Fi. Our battery is at 16%. It's not charging right now, and so on, just all the data. We can also stream our raw brain waves. Basically, similarly, we connect and we log in. Then we say Neurosity.brainwaves raw, and we pass it a function that we create here, on raw, which takes epoch, which is going to be a dictionary containing a bunch of values, and we just print it to the screen. We'll see what that will do. Then we say here, just while true, sleep for half a second and then continue, sleep for half a second and continue, and so on. So let me just click this. No, let's run this code. Let me just turn it off. So this doesn't look very meaningful. Obviously, it's just a bunch of numbers for what a level of activity each channel is picking up. It's not very useful because, well, how are you going to make sense of it? But the point of streaming it raw like that is that maybe you will use some kind of machine learning then, after you have this data, to make sense of it. So for example, the idea with machine learning generally is I will give it a lot of examples at first where I will say, look, when my brainwaves had these numbers, I was sad. When they had these numbers, I was happy. Like maybe 1,000 examples of each. And then 1000 the first time on a new kind of data, I will say, based on my brain waves, am I sad or happy? And it will be able to tell me if I'm sad or happy. That's the idea with machine learning. Like just throw it a bunch of examples, and it will figure out the general logic with which it will be able to tell you for new examples that you haven't shown it, what kind of situation is going on. All right, now to see what's going on, let's look at just one. So here we have the channel names, label, which is in our case raw, because that means just raw brain activity. This is what millisecond it happened at. And yes, it's just our raw data. Not very meaningful, but could be meaningful if you pair it with machine learning. Now, more importantly, let's see how we would measure our focus level or calmness level. Well, let me see what's happening in the chat. Oh, yeah. So, for anyone who's not checking the chat, Etuna asked the price of this thing, how much it costs, and if you need some kind of license or some permission to have it. So there's different kinds of devices. Some do require a license, but basically they pretty much only need a license if they're invasive. So if you had to drill through your skull to put it in. For non-invasive ones like this one, you don't need a license. Anyone is free to buy them if they have the money for it. And this one particularly costs $1,500. There are some versions that cost $200, some versions that cost $500 or $1,000, and some that even cost like $10,000. But the typical consumer level ones are from like $1,000 to $2,000. That's the range for most of them. But I mean, there is this Muse headband, which, yeah, there is a $500 version, but I believe there is, yeah, the Muse 2 is $250. So, yeah, I mean, reasonably cheap ones exist as well. But yeah, I mean, the more expensive it is, basically more accurate it is and better it is. So this one costs $1,500, and you are allowed to have it if you just buy it. Yeah, you can buy it just straight up from their website. Like, you just go Neurosity Crown. You can just pretty much buy from them. They'll ship it. You can use Inex or well, whatever. Basically, yeah, you can buy it, and yeah, it's legal. It's fine. You might not be allowed to directly sell it as a business. You might have some regulations there because maybe human brain data is private information, personal information, I mean, but generally to experiment on your own, it's completely fine. You don't need a license. Yeah. So let me just get back to the topic, and thanks for the question. And if you have any other questions, also feel free to ask. So as I was saying, as before, we get the libraries that we need. We connect to our Neurosity Crown at this device name and email and password. And then we define what we want to do if we detect focus and what we want to do if we detect calmness. We subscribe to focus and to calmness. And what subscribe means is that basically, like 250 times per second, this device emits information. So it throws out information, for example, about focus, about calmness, about raw brain activity, and so on. Some metrics it throws out less frequently, some more frequently. And if you subscribe to one of those events, then every time it's emitted, you will hear it. So in our case, for example, we are subscribing to the focus and to calmness. And subscribing just means that basically this on focus function will be called every time this device throws out a focus measurement. And here I just said, let's print it to the screen. And on calmness, for now, I have it commented out, so I won't be doing anything. But yeah, and also we get this unsubscribing to handle so that we can close this connection after we are done with it. So if you remember from our previous Python lecture, sometimes we have to close the connections ourselves so that this doesn't remain open and doesn't drain battery or doesn't take up space. So let me just run this. So here we can see we are getting, oh, you're focused. Now your metric is awareness. And it's a probability of 26% that you are focused, probability of 50% that you are focused, and so on. So basically, higher number would mean better focus, lower number would be worse focus. And similarly, we can maybe now ignore focus measurement and instead print calmness measurement. Like, let's see what this will do. So basically this, I might need to adjust the device a little bit more in my head, but the basic idea is it can roughly measure how calm I am. And you don't necessarily have to go all the way to 1. This will be less precise like that, like 40% here might already be good enough. And by the way, I mean, if you want this to be a percentage instead of this number, you can easily do that by just literally multiplying it. So we can say probability times 100. And if we print it like this, it will be a percentage instead. Instead of 0 point something, it will be what percent you are calm, basically. And right now I'm not calm, obviously, because I'm not relaxed. I'm speaking and I am explaining a lecture. But like if I were to relax, like you can see, when I start to calm down, the calmness level goes up. But as I speak quickly, you can see that as long as I'm speaking quickly, this calmness level is low. But if I shut up right now, it starts to overall go up, basically. And then what you could do is maybe if you are calm enough for a while, maybe you give yourself some kind of a prize. Like maybe here we will say let's say calm count is 0. And let's say some calm limit or calm minimum of 0.3. And let's say if you are at least 30, let's even just say 30. So if you are at least 30% calm on this calmness level, you are calm enough. And let's say that if your probability of being calm is more than or equal to calm minimum, and we increase your calm count, and if your calm count, let's say, exceeds 5, wow, you are very calm, will be printed on the screen. And if you're not that calm, then your calmness will reset. And now let's see if we can get it to detect longer periods of calmness. I'm getting a little bit annoyed it's slightly losing and then it's affecting me. Let me just move the barrier down a bit, cheat on this, like move it to 25%. So battery. It could be. So I believe our battery died. Yeah, I mean, how to fix this issue. Sometimes it overheats and then battery dies quickly. I'll look into why that was. But basically the idea is once you have this kind of bridge, you can try to figure out creative uses for it. It can be therapeutic, like helping someone to overcome their fear or anxiety or inability to focus by gamifying it for them. Or it can be just for fun in games, or it can be just to learn some new thing about the brain. Like maybe we will try to learn how it shows up in your brain activity when you lie, how it shows up in your brain activity when you think of elephants or when you think of running, and these different kinds of things. So the idea is, yeah, this is all possibilities that this kind of device allows us. But this technology is still very much in early stage, which means that most of your work will be research work, not building a product on top of it, because you could build a product on top of it, but it's very early stage for it, basically. Another thing that we can do with this device, just one more thing that we haven't covered. Let me just plug this device in meanwhile. It's called kinesis. So, like telekinesis, this kind of thing. Basically, this is a feature of this device that you can figure out which part of your motor cortex is active, and based on that, realize, am I thinking of moving my right arm? Am I thinking of moving my left hand? Am I thinking of moving my right foot? Am I thinking of chewing? Am I thinking of jumping? And based on which movement you are imagining, you can trigger different kinds of code. So here, we were triggering this code based on calmness or focus measurements. And if I am calm enough, I will print something on a screen or take a screenshot or send an email or whatever we can do with code. And with code, we can basically do anything, including, for example, ordering a robot arm to move a certain way or ordering a robot car to move in a certain direction and so on. This just depends on our creativity. And similarly with kinesis, so here is what we do in this simple example. So again, we import the necessary libraries. We define which label we want. So in this case, we do left arm. They have a couple different labels, as we can see here. And just wait. Okay, it's not letting me because it's disabled right now. But basically, they can do left arm, left foot, right index finger, left toe, whatever it is. And you would first come to this place. You would train it. Training just means for like 5 minutes, it will tell you, think about moving your left arm. Now don't think. Now think about it. Now don't think. It'll repeat like that for 5 minutes, just so it can have examples of what your brain looks like when you are thinking of your left arm and what your brain looks like when you're not thinking of it. From there, with machine learning, it will figure out, on average, how to determine if right now you are or are not thinking about it. And then in your code, you can just say neurosity.kinesis with this label, which is left arm in this case, on kinesis, this function. And every time your this device detects that you were thinking of moving your right hand or left hand in this case, this will be triggered. This function will be called. It will get the prediction being in this case that you are moving your left arm, and probability, how accurate it is in its opinion. And then you can say, if it was more than 90% likely, then do some action based on it. And then this allows us to take a screenshot, shrink a tree, or whatever we want. For instance, one thing that I did with this, let me just show it briefly, was that I made this simple game where, based on the readings on this device, if you are focused enough, basically, if you remain focused, the trees will keep growing. And if you lose focus, the trees will shrink. Like now I am losing focus and the trees are shrinking. And this is a simple example of neurofeedback, because if a person was to play this kind of game for enough time, this person would figure out how to intuitively control his focus level, which could then help with studies, work, and or maybe with managing the ADHD. So this is the idea. A lot of this is still experimental, and what I'm showing you is basically tip of the iceberg. There's a lot of machine learning, AI, and just more complicated signal processing to it as well. But yeah, this is the kind of thing that exists, and this is how we can basically do it with code. We can, after we have these signals received, we can use it in as complicated of use cases as we can think. In games, in medicine, in controlling some robot arms or cars or whatever we can think of. Like some people even have this idea that maybe I will somehow figure out how to turn my thoughts, this brain activity, into a right kind of prompt for ChatGPT. And then I can use ChatGPT to draw an image based on what I am thinking. So for instance, if I am thinking of left, maybe I'll draw a dragon pointing left. If I'm thinking of right arm, I'll draw a dragon moving right or whatever, something like that. The idea is as far as our creativity can take us, we can use this the same way we would use input from our keyboard or mouse, which is basically all kinds of input. Okay, so this is just the main stuff that I wanted to show for today. And with this, we basically conclude our lecture series. The only thing that's in front of us from now is just the final projects that we will have. Nina will explain more details about them. But yeah, after those final projects, this cohort will be over. We are thinking in the future of possibly expanding to include more activities other than the cohort. But for now, yeah, this is basically the end of this cohort. So if you have any questions or suggestions or anything, either now or later in the chat, feel free to voice your opinions. And yeah, that's basically it for today's lecture. What do you think?
I have a question.
Yeah.
Will we everyone be able to register for next cohorts?
If you want to, yeah. No constraint on that, yeah.
Oh, okay. Thank you.
Yeah, so like keep in mind a few things. Let me just see this. So Nina and I will discuss about like exact formats for the projects, and we'll give you the details like today or tomorrow, and we'll present them in 1 week or 2 weeks, depending on the complexity of the projects. So yeah, either next week or the week after that, we will have the presentations of the final projects, depending on how difficult we make them. Thanks everyone for the kind words. That's nice. Thanks. And yeah, so what I wanted to say is every lecture that we have, we try to upload on YouTube, like unless there is some technical difficulty that stops us from it. I will also upload this lecture on YouTube. Also, our homeworks are available on Drive if you want to, and in Discord if you want to go through them again. And yeah, even with that said, yes, if you feel that you would rather maybe go through this stuff again, you can register on the next cohort when we start the next cohort. And also, some of you, if you are willing to volunteer, you could, like, we can discuss this in person, but we could maybe have you collaborate on the next cohort. Like, even in this cohort, one lecture, as you remember, was from an alumni from the previous cohort. So we could work on that. We could help you with structuring the lecture and such. Aside from that, in the future, we do have some plans for maybe a neurotech hackathon, maybe an Olympiad, maybe that kind of things, maybe even research. But those ones require a different kind of organizing and resources, and basically we're working on it. We can't promise you the exact timelines on those, but yeah, that's basically it for this course. All right. I'll see you in the next weeks about the final projects. And yeah, for now, goodbye. And nice to meet
Thank you. Bye.
Thank you. Goodbye.
you.
Goodbye.
Bye.